Hi everyone! Welcome to part 4 of our lecture on chemical equilibrium. This will be our last lecture in this chapter. Today is a very math-heavy lecture, so be prepared for lots of math coming your way. It may be helpful to have a calculator and maybe a pen or pencil to go ahead and work through some of these problems with me so that you know how to do them when you are on your own. So here we go. Okay, so we can use stoichiometry to determine the equilibrium concentrations of reactants and products if you know initial concentrations and one equilibrium concentration. Okay, so we've talked about thus far how equilibrium related to, last chapter, right, our kinetics. And I said that, when you put in initial amounts of your reactants, right, they will react. Eventually, they will form products, and we'll get to a point where the rate of the forward reaction is equal to the rate of the reverse reaction, and then the concentrations of the reactants and products remain the same because the reactants are making products just as fast as the products are making the reactants, so they stay the same. Okay, so if we know our initial concentrations and one equilibrium concentration, then we can go ahead and calculate the other equilibrium concentrations. And the way that we will do this is we will set up an ICE table. We've already looked at how to use ICE tables when we are dealing with reactions, right? That's when we were talking about looking at the limiting reagents and how many moles of product we can make. We're going to do a really similar thing here. The big difference is that when we do equilibrium ICE tables, we're going to make sure to always do those in molarity. Whereas when we were doing reaction ICE tables, we made sure to always do them in moles. So that's the big difference here. Once we know our, that final equilibrium concentration of one of our either reactants or products, it doesn't matter. But once we know one of the equilibrium concentrations, we can use that to figure out what X is, right? What that change is. And then we can use that and apply that change to all of the other substances. Okay, this will make more sense, I think, with an example. So let's go ahead and try it out. So in this reaction, we have iron, we have thiocyanate, and we are making iron thiocyanate. Okay, so we have 6 molar iron and 10 molar thiocyanate, and we mix them together. Okay, so we're starting with just reactants, which is kind of typical, right? So we dump in our reactants, and I say at equilibrium, I know the concentration of iron thiocyanate is 4 molar. So I want to know then, what is the value of the equilibrium constant for this reaction? So I know how much I started with, okay, and I know how much I ended with of one of them. But if you think about this, right, if we're going to find the value for the equilibrium constant, then we need to know the molarities of all of them because our K value, right, our K value is going to be products over reactants. So it will look like this. Okay, so that will be our K value. So we know this value up here, and we know what these started as, but we don't know what they ended up as. So we're going to use this final concentration and the two initial concentrations to figure this all out. So the best way to start off is to fill in the ICE table with what you know. So here's our reaction. We're making an ICE table. Okay, and you'll notice this now says equilibrium rather than saying end because this is a reversible reaction, right? So we only ever get to an equilibrium. We don't get to like an ending point, just kind of, there will still be reactants and products left at the quote unquote end of the reaction, right? Because it doesn't ever reach its end really. Okay, so let's fill in what we know. So we know our initial concentrations of these guys, right? We have 6 molar iron, 10 molar thiocyanate. And again, these are being done in molarities, not in moles. So right now, our volume doesn't matter. These are just concentrations. We know the ending concentration of our iron thiocyanate. Okay, so we can use this to figure out our other equilibrium concentrations. Because if you think about this, right, our change, this is going to be done just the same. We're going to write minus x plus x. And the reason that I know my reaction is going this way is because we have 0 molar of our product to start with. The only way it can go is to the right. It couldn't go left. It can't, it doesn't have any products to, do anything with. So it has to go to the right. It has to go make some products because we are starting with 0. So that means our reactants are going to get minus X and our product is going to get plus X. Remember, we're using the coefficients here. They would go in front of our X's. So it might be, like if this was like a 2, then this would be minus 2X, but it's not. Okay, so all of these just have 1s, so it's all just minus X and plus X. Okay, so we know that if we think about this as an equation, 0 plus X equals 4. Easy math to start with, right? So therefore, X is equal to 4. So we can go and, we can use this to fill in all of these change values. So we know that that's going to be plus 4. Therefore, this was minus 4, and so was that, right? Because we're just filling in these X's. So now we can go ahead and calculate the equilibrium concentrations by adding together, right? Remember, always initial plus change equals equilibrium. So 6 minus 4 will give us 2, 10 minus 4 will give us 6. And now we have all of our equilibrium concentrations, and now we can put them or plug them in to our mass action equation. So there it is. We're just going to plug in those values, and then we will get a number. Okay. Just to point out, remember that K is unitless. So I know it looks like our molars don't cancel out, right? All of our molarities. That's okay. Fill them in anyways. K is unitless. Okay, so if it makes you feel better, just don't put your units in there. And look, now there's nothing to cancel out. Okay, so just to point out, when we look at this, K is essentially, or almost equal to 1. This is a really small value of K. That's why we have rather large amounts of both products and reactants, or approximately equal amounts of products and reactants. It may not look very equal to you at the moment, but you'll start to see in later examples that this really was quite equal. Okay. Since it is slightly less than 1, our equilibrium lies slightly with our reactants, but it's pretty darn close. Okay, so that would be if we knew one of the equilibrium concentrations, right? So in the problem, we knew one of our equilibrium concentrations that was given to us, and we were able to use that to figure out our other equilibrium concentrations. Sometimes you won't be given that, though. Sometimes you will just be given a mixture of reactants and products, okay? And they'll, and the problem will say, here's your mixture of reactants and products, here's your K value, and can you figure out what all of the equilibrium concentrations are? Okay, but sometimes your reaction will already be at equilibrium. And so we need to figure out, okay, when I have this mixture of reactants and products, is it at equilibrium? And if it's not at equilibrium, which way does the reaction need to shift? Does it need to shift to the right, or does it need to shift to the left to achieve equilibrium? Okay, and the way that we are going to figure all of this out is we are going to write the reaction quotient. Okay, and the reaction quotient is essentially exactly the same thing as our equilibrium expression. The only thing that's different, literally the only thing, guys, is you write the letter Q instead of the letter K. Everything else is the same, okay? We're still going to write the ratio of the products raised to the power of their coefficients over the reactants raised to the power of their coefficients. It is the exact same thing. So if you look at this reaction, right, we have our products are going to go on the top and the reactants are going to go on the bottom. So whether it's QC or just Q, right, sometimes we'll leave off that C because its concentration is just implied, or QP, it doesn't matter. It's still products over reactants. The only thing that's different with the reaction quotient instead of the equilibrium expression is that all we did, we switched out the letter Q for the letter K. K implies it is at equilibrium. Q implies we don't know what it is. It could be at equilibrium, that we just have stuff, right? And so we're going to compare Q and K. If Q and K are the same, then it's at equilibrium. Great. But if Q and K are different, that's when we start to have to figure out, okay, is it going to shift left or is it going to shift right? Okay. So the first thing you'll always do when you're approaching an equilibrium problem is to plug in all of your numbers for Q. Right? You're going to plug in all of these numbers and then use that to calculate Q and see what is Q. And then we can compare Q versus K. So if Q is equal to K, then the system's at equilibrium. Then you're done. Done with the problem. Woohoo! Easy. It's pretty rare. Otherwise, there'd be no point to the problem, right? So then if Q is greater than K, so if Q is too big, again, remember, whether it's Q or it's K, it's always products over reactants. So if Q is too big, right, Q is greater than K, Q is too big, then that means there's too many products. So if there's too many products, right, if we have, reactants and products, if there are too many products, then our reaction needs to shift to the left to use up some of those products to make more reactants so that Q and K will be equal. Okay, so it'll keep shifting left until equilibrium is achieved. The opposite is also true. If Q is less than K, again, products over reactants. If Q is too small, that means we have too many reactants. Okay, so our equilibrium or our reaction will need to shift to the right to achieve equilibrium. Okay, so you're always going to, whatever you're given, right, your starting concentrations, the first thing you're going to do, calculate Q. And then you're going to see, okay, how does Q relate to K? Is Q equal to K? Great, I'm done. Is Q bigger than K? Right? Then we're going to shift to the left. If Q is smaller than K, then we're going to shift to the right. So that's really the first step. Okay, so we're going to go through all the other steps. So the first thing would always be, write the balanced chemical equation. Usually this will be given for you. If I, decide to be really mean and make you write it yourself, then you can do that. Just always double check and make sure it's balanced. And then you're going to write the equilibrium expression or that mass action equation, right? Q is equal to whatever, right? Products over reactants. And then you're going to list or calculate the initial concentrations or pressures. The reason I say that you may need to calculate your initial concentration is I may give you moles and liters. And so you just will divide them up to get the concentration, right? Moles over liters. Sometimes I'll give you the molarity. Sometimes I'll give you moles and liters. Just pay attention because remember, you need to do equilibrium ice tables in concentrations, not in moles. Okay, so then you would fill that in for your I. Right? And sometimes there will be products present initially. Sometimes there will just be reactants, like you put reactants in and your products are 0. So in that case, your reaction will always go to the right because you have to go make more products. But if there are products present initially, you need to figure out which way will the reaction go. And that's the whole Q versus K thing. Will the reaction go to the left? Will the reaction go to the right? And again, calculate Q first just to make sure it's not already at equilibrium. If it is, you're done. But if it's not at equilibrium, then again, you're going to figure out, okay, is Q bigger than K or is Q smaller than K? What does that mean? Which way do I go? And so if it's not at equilibrium, like I said, then you're going to figure out which way it will go. But there's sometimes that you will actually need to deal with a reaction first. And we're going to see an example of this. And if that happens, then lucky you get to make 2 ice tables. Not 1, but 2. Because there are some scenarios where you'll need to deal with the reaction, like we talked about before when we were talking about the molarity of leftover ions and looking at how much product is formed. And then you'll need to do another one for once you get to equilibrium. Okay? So we're going to see a bunch of different examples just to see the different ways that this shows up. Regardless, though, if Q is not equal to K, you're going to have to set up an equilibrium ice table to figure out those equilibrium concentrations. Again, I think this is going to make a lot more sense with some examples, so let's go ahead and go through this. Okay, so first thing, set up an ice table. Then compare Q to K, figure out which way it's going to go. And then you're going to define everything in terms of X, just like we've done, right? The minus X for the substances that are going to, lose, that we're shifting away from, and then the plus X on the side that we're shifting towards. And then you're going to solve for X. And so I will show you how to do all these things. Let's go ahead and check it out. Here's a problem. Consider the reaction at some temperature. So there's your reaction, and you are given a K value. This is very common in equilibrium problems. Oftentimes, you are given the K value and you are asked to solve for the equilibrium concentrations. So here we go. Assume you're starting with 0.095 molar of COCl2. And I want to know how much of each of these are present at equilibrium. Let's not do molecules though. Let's ask, what's the concentration present at equilibrium? And again, we've already used ice tables for limiting reagents and molarity of leftover ions. So if you haven't watched that lecture, do that first and then come back to this. But now we're going to figure out how to use ice tables to solve for equilibrium concentrations. So here it is. The first thing you should always do is write the law of mass action, right? Write that Q term or that K term. So here it is. We have our K value, right, is here, is equal to our products over reactants. And they would be raised to the power of their coefficients, but they don't have any. So there's no point in writing ones. Next up, we're going to ice the problem, beginning with all of the initial concentrations. So our initial concentration is there, and we don't have any of the products. Okay, so again, we know that this reaction is going to have to go to the right to make some products because it can't go left because we don't have any products to work with. So it has to go right. So for our change, we're going to go minus x plus x plus x, right? Some of this is going to get used up going that way. So it's going to lose some of its concentration and the others will increase. And then again, initial plus change is always going to equal equilibrium. So we are going to add these straight down. So there you go. Okay, so now we've filled in our ice table. And this is very typical for an equilibrium ice table. Okay, we have, something minus x and we've got some x's floating around as well. So now what we're going to do is we are going to take these equilibrium values and we are going to plug it into our mass action expression so that we can solve for x. So let's see what that looks like. Actually, here, I'm going to skip forward for this one first. And then I'll come back to that other slide. So here it is. Here's our equilibrium values. And we are going to plug them in to our mass action expression. So there we are. So we've got x's on the top for our products, and we have our reactants on the bottom. Okay. So now I'm going to go back to this previous slide and talk about this. Okay. If K is very small or very large, so if K is very small, I'm talking like times 10 to the minus 3 or smaller. So maybe it's, times 10 to the minus 6 or something like that, right? Really, really small. Or very large. So again, times 10 to the 3 or larger. Then we are going to assume the x is negligible for the changes in concentration. So that means that this, right, if we have an initial concentration and we're subtracting x, that change in concentration is so small that our equilibrium concentration is essentially the same as our initial concentration. If you think about sig figs, that's where this comes into play. If we think about significant figures, right, usually when we do the subtraction here, this x is so small that it makes it the same when we round for significant figures. Okay, so if we have a very small k, for example, that means that there are mostly reactants still at equilibrium. Okay, your reaction didn't go very well. That minus x term is so small that it doesn't even change the concentration really with respect to the initial concentration. So the initial concentration's very, very little from their final concentrations. The difference is negligible. And I know some of you are probably thinking, well, I like to be precise, right? I want to go through and calculate what this x might be so that I can plug it in so I can know exactly what the concentration is, right? I understand. The benefit, though, is that there is no quadratic equation involved in solving it this way. Okay, and we will see that there's a way that you can check and make sure that this assumption is valid, right? The difference will be negligible though. Like if you go through and calculate it with respect to significant figures, oftentimes it doesn't change the value whatsoever. And even if it did, it would change it less than 5%, which is negligible. Okay, so this will work for very, very small values of K and very, very large values of K. All right, so let's go ahead and look at this. So we plugged all of these values in, and if you look at K here, it is very, very small, times 10 to the minus 10. This meets the criteria for using this approximation. So instead of this term being on the bottom being 0.095 minus x, we are just going to use it as, I thought I had that there. We're just going to use this as x times x, which is x squared, right, over 0.095, like that, okay? So we just get rid of this x term because the difference is negligible. This is going to make our equations much easier to solve. So if you went and looked through, right, otherwise we would end up with x squared on the top, we would have a minus x term, right? We would have to use the quadratic equation that, x equals minus b, right, all that good stuff. Okay, so here it is. So again, we're going to assume this change is negligible. We're just going to go ahead and get rid of that minus x so that we can solve the problem. Then we can multiply both sides by 0.095 and take the square root so that we can solve for x. When we do that, x will be 4.5 times 10 to the minus 6 molar. Okay, so if we were to then go through and solve for our equilibrium concentrations, right, at equilibrium, our carbon monoxide and our chlorine are both equal to x. So therefore, x is the equilibrium concentration of those two substances. Okay, now when we look at our COCl2, right, our equilibrium concentration would be 0.095 minus 4.5 times 10 to the minus 6. Okay, looking at significant figures here, we can only have up to three places past the decimal in our answer. So if we went through and did this subtraction, it would round back to 0.095 because the difference here is negligible. It's important when it's looking at these, right, because their initial concentration was 0. So nothing compared with something, that's not negligible, right? We went from nothing to having something. So this x we can't cancel out because it's important. But the difference here, right, the difference in the concentration, that is what's negligible. So that is what we can cancel out when we're solving these types of problems. Okay, we can go through and actually check to make sure that it's okay that we did this, right? I told you, like, rounding for significant figures, it will work out okay, but just to double check. So our criteria is that it needs to be less than 5%, right? That change needs to be less than 5% of our initial concentration. So our initial concentration was 0.095, and our change was 4.5 times 10 to the minus 6. So we're going to put our x on the top over our initial concentration on the bottom, and then multiply it by 100 to see the percent. Okay, as long as that number is less than 5, you are good to go, and this approximation is totally fine to use. If it's greater than 5, likely you did something wrong. I typically do not write equations where you're going to need to use the quadratic equation. It's just, it doesn't show up very much in the real world in chemistry. So typically, I will write problems that will allow you to use the approximation. Not always, but oftentimes. So if you're getting something over 5, you probably did the problem wrong, and I would go back and try and do it a different way. All right, let's go ahead and go through some practice problems. I have 3 practice problems. At any point during these practice problems, if you feel like you can pause and try and work through it yourself, I would recommend that you do so. The Chapter 15 lecture worksheets have lots of equilibrium problems on them, though. I feel like these problems take a lot of practice to start to get really good at, so I've included a lot of practice problems in your lecture worksheet. So if you don't feel comfortable doing them yet, go ahead and keep watching and get more comfortable, and then go practice it there. All right, let's go ahead and try this one out. We have 4 moles of HI are placed in an evacuated 5-liter flask and then heated to 800 Kelvin. System's allowed to reach equilibrium. What is the equilibrium concentration of each species? So at the beginning, all we have are reactants. We don't have any products. And if you'll see, I gave you moles and I gave you liters, Remember, we're going to do an equilibrium reaction or an equilibrium ice table, so we need to have it in molarity. So the first thing you'll need to do is go ahead and calculate the molarity, right? Molarity is equal to moles over liters, so you're going to divide those up. 4.00 moles over 5.00 liters. That gets us 0.800 molar. So we need to do that first. But when we do this, right, so we have, 0.800 molar, and we have 0 and 0. So we know that our equilibrium, right, our reaction is going to have to shift to the right because we don't have any products. It can't go left because there's nothing to use up. Also, what I want to point out to you here, K is not very, very small or very, very large. K does not fall into the criteria for using the approximation. So we can't cancel out our x's along the way, so I'll show you how to solve this type of problem. But just so you know, you aren't going to have to use the quadratic equation on this one either, which is really awesome. So let's see how this plays out. First thing we need to do, make our ice table. So we have our initial concentrations, and then our change, right? Our change will be minus 2x, because again, we need to use that 2 here, and then plus x and plus x on the other side. We're going to, have minuses for what's getting used up, pluses for what's being added. And then for our equilibrium, we're just going to add those straight down. Okay, so the next step will be to write that mass action expression, right? So we're going to go ahead and write, our products over reactants. So we have hydrogen times iodine over hydroiodic acid squared, right? Remember to raise them to the power of the coefficient. That's how that 2 got there. So then we can go ahead and fill in our equilibrium values. So we're going to take all of these and plug them in. So we got x and x for both of our products, and then we have 0.8 minus 2x squared on the bottom. Again, don't forget this. People will oftentimes leave it out, or they just kind of lose it along the way. It's important. Don't lose it. All right, so once we've got that, we can actually combine those x terms. Okay, and so once we do that, right, instead of writing x times x, if we write it as x squared, this should show you how we're going to solve this problem. Okay, because again, we can't use the approximation because k is not very, very small. It's kind of small, but it's not very, very small, so we can't use it. What we do instead, though, since we have squared on the top and squared on the bottom, we can take the square root of this whole thing. And once we take the square root of both sides, right, that got rid of the squares on the top and the bottom, and it made this problem much more manageable. So now we're going to multiply both sides by 0.800 minus 2x. And when we do that, right, these cancel out. So then we're just going to be left with x on that side. So then we can distribute that 0.126 in, combine our x's, and then divide both sides by 1.252 to get our value for x. Okay, so I'm going to let you can, go through that algebra if you'd like, but it's just solving for x. So now once we have x, remember that you're not done, right? Because you need to solve for the equilibrium concentrations. So our concentration of hydrogen and iodine, those are both x. So we just solved for x, so that's the concentration of both of those. And then we can plug it in for HI, right? We have 0.800 minus 2x, so we're going to plug in that number for x. So it's going to be 0.8 minus 2 times 0.0807, and that gets us 6.39 molar. Okay, so again, these ones were equal to x. This one, I just plugged in x into our equation up here. Okay, so again, be careful with this whole approximation business. If it's not very, very small or not very, very large, you can't use it, but oftentimes there's a solution other than using the quadratic. Okay, let's try another one. Ammonia undergoes hydrolysis according to the reaction below. And I want to know the concentrations of everything in a solution that was originally 0.2 molar of ammonia. So again, we only have our ammonia. We don't have any of these. Okay, so we have 0.200 molar ammonia. And again, it's already in molarity, which is nice because that's what we needed to. But you'll notice we didn't say anything about water. Well, the reason is water is a pure liquid. Okay, remember, pure liquids and pure solids are not going to play into our equilibrium calculations. So you're essentially just going to ignore it. Pretend like it's not there, right? It's not going to end up in our mass action expression. It's not going to end up in our equilibrium calculations. All right, let's go through this. So we have our initial concentrations. Okay, and so now for the change, we know that this reaction is going to have to go to the right. Right now we only have reactants. It has to go to the right so that we can make some products. Can't go left. We don't have any products to start with. So we're going to write minus x plus x plus x because nothing has a coefficient, so we don't need anything in front of the x. And then again, always initial plus change will give us equilibrium. So we'll just add those straight down. Okay, and now we need to write our law of mass action, right? Our mass action expression. So we'll go ahead and fill that in. Products over reactants always raised to the power of their coefficients. Here, since all of the coefficients are 1, we didn't raise to the power of anything. So then we'll write our equilibrium concentrations. So we fill in our x's for our products and our 0.200 minus x for our reactant. K is very small in this case, right? Like I said, usually it's anything smaller than times 10 to the minus 3, and times 10 to the minus 5 meets that criteria. So we can use the approximation. Yay us. Okay, so when I use that here, all that does is that gets rid of this minus x term on the bottom. Okay, so that goes away, and I'll combine our x's so that it's x squared on the top. Then we'll multiply both sides by 0.2. We'll take the square root of both sides, and we have our value for x. Okay, since we used the approximation, right now is a good time to go through and check to make sure that we could have done that. So the way that we do this is we put our change on the top, right? Our x value goes on the top, and our initial concentration will go on the bottom. Okay, so our change over our initial concentration, multiply that by 100, and we get 0.95%. Therefore, this approximation is valid. We are good to go forward. Now, all we have to do is plug in our x value for our equilibrium concentrations. So both of our products are just x at equilibrium. And then since we used the approximation, right, 0.2 minus x, if we went through, and we can plug this in, if we use the approximation, right, you see that these are very, very similar. Okay, but I'll go ahead and plug it back in here just so we get closer to the right answer. Okay, so always go through, even if you use the approximation, plug this back in as x to figure out our final concentration. So, and then these guys, these were just equal to x. Okay, last one. This is the most fun one. So make sure you're really paying attention. It's got, some twists and turns. So hydrogen reacts with ethene to give ethane according to the reaction below. If you remember your organic chemistry from Chem 1, ethene tells you there's a double bond, and ethane tells you there's a single bond. You can go back and review that if you'd like. You don't need it right now, though. But when I want to calculate the concentrations of everything in a mixture that originally contains 0.18 moles of hydrogen, 0.155 moles of ethene, and 0.250 moles of ethane in a 1 liter container. Okay, so if you'll see, we have starting amounts of everything. 0.180 moles, 0.155 moles, and 0.250 moles. Okay, and these are all in a 1 liter container, so our moles and our molarity will be the same, which is really nice so that we're not trying to convert between them. So I'm just going to leave units off for now because sometimes they'll be used as moles and sometimes they'll be used as molarities, but I will tell you which one I'm using at a given time. But as you can see, we have amounts of our reactants and our products to start off with, okay? And then if we look at our K value is gigantic, like huge, 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 right? I told you we can use the approximation over times 10 to the third, and I told you that counted as very large. This is like very, 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 very large, okay? And what this tells us is the reaction really goes to completion. The reaction almost totally makes complete products. There's going to be very, 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 very little reactants left, Okay, so now if we look at this though, look at all these numbers. That's not being reflected in what we have here, right? This is not gigantic amounts of products and teeny tiny amounts of reactants. This is really approximately equal amounts of everything. And what this tells me is it's not going to be enough to simply solve for the equilibrium. We need to deal with a reaction first before we can deal with the equilibrium. Okay, so the way that we are going to do that is we are going to do a reaction ice table in moles to deal with the reaction that happens first, right? Because there's a bunch of this and a bunch of this, so they're going to react together to make ethane. Okay, so we need to deal with, okay, well, how much are these going to react first to make ethane before we can deal with, okay, after the reaction happens, what does it look like at equilibrium? Because right now, you can think about as, you know, we just dumped a bunch of all this stuff in here. We need to have that initial reaction first. The forward reaction is going to happen much faster than the teeny tiny reverse reaction until they get to this point of equilibrium, okay? So, like I said, K is super large, which tells us there's mostly products at equilibrium. And right now, we only have reactants, but we have both. Okay, we have reactants and products. And really, we need to have mostly just products. So we need to do a reaction ice table first before we can do that equilibrium ice table. This one will be in moles because this is a reaction. When we do equilibrium, it's going to be in molarity. But like I said, because the volume is 1 liter in this problem, the numbers will be the same. Okay, so we're going to go through our initial amounts of moles for each one first. Okay, and then for the change, if you'll recall from when we did, the reaction ice tables in that separate lecture, we needed to figure out which one of these was limiting. Okay, so we're going to do minus x. This should be minus x. My apologies. Both of those should be minus x, and then we have plus x. But we don't know what x is, so we need to figure out what x is. And the way that we do that is we're going to assume each one of these goes to 0. We're going to assume this is 0, and we're going to assume this is 0. So we're going to write two different equations. 0.180 minus x equals 0, which tells us that x is equal to 0.180, or 0.155 minus x equals 0, so x equals minus 1, or x equals 0.155. Okay, so this one is assuming hydrogen is limiting, and this one is assuming ethene is limiting. Okay, so we look at which one is smaller. So ethene gives us the smaller value of x, so that is the one that we are going to use as x. Okay, we can't use this one because it's in excess. So we're going to plug that in up here. So our change is going to be that 0.155. So we're going to subtract it from our reactants and add it to our products. And when we do that, now we have our equilibrium values, or our end values, really. Okay. And so after our reaction, we have a little bit of some of the reactants, we have none of this one, and then we have products. So this is assuming our reaction went to completion. It went to the right as far as it could, because like I said, K is really, really, really big. So our reaction is going to go mostly to completion. It's going to make mostly products and have only a very small amount of reactants left. But now that we've calculated the reactants and products left after the reaction, now we can deal with the equilibrium concentrations. So the equilibrium is going to shift back toward the reactants. So the equilibrium will go this way. And I know you might think that's weird. You're like, well, but we just spent this whole time making the reaction go toward the products, right? You just said K is really, really big, so it makes a lot of products. I did. But when we do this whole minus x plus x business, right, it can't go to the right any farther. We made 0 ethene. Okay, we're at 0. It can't go to the right anymore. So when we're looking at this equilibrium, the only way that it can go is back to the left. Okay, so when we do this ice table, we're going to shift back to the left a teeny, teeny, tiny amount. Okay, so our initial concentrations, right, remember these were in moles, but since we're in a volume of 1 liter, we're going to use those same numbers because they're the same as molarity. Okay, so I'm going to write that this is in molarity, whereas this was in moles. Okay, so now we're going to do that plus x minus x business. So we're shifting back to the left. So our reactants are getting plus x, our product has minus x. And then our equilibrium, we're just going to add those straight down. Okay, so now we can go through and just solve this just the same as we've been doing any other problem. We're going to take these equilibrium values and we're going to plug them into that equilibrium expression to start to solve for x. So here it is, products over reactants, right? So we'll take our products, put that on top, our reactants will go on the bottom. Okay, nothing's being raised to the power of any coefficient, or because we don't have any here, they're all ones. So we can just go ahead and plug them in. So just copying this forward. Okay, so now, again, K is very, very large. I told you you can use the approximation, anything over times 10 to the third. Okay, times 10 to the 18 way exceeds that. So we can use the approximation and get rid of all of the changes in concentration. So we can get rid of the minus x and the plus x. Remember, you can't get rid of this x because our initial concentration was 0. So compared to 0, anything is not negligible, right? Anything is important. So we can't get rid of that x. That's the one that's got to stay. Just the changes in concentration we can get rid of. So now we can go through and start solving for x. So I simplified 0.405 over 0.025, and then we're going to go ahead and rearrange to solve for x and calculate it out. So this, if you look, that's a very small concentration, right? Very, 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 very teeny tiny. And again, like I said, that's what we expect. It's mostly products at equilibrium. So the fact that that's what x is, that teeny amount of our reactant that we had left, that makes sense. So we're going to, though, double check our approximation. So we have our change over our initial concentration. And I always pick the smallest initial concentration down here just to be sure that this, this approximation really will work for all of our concentrations. Pick the smallest one. So we have our change over our initial concentration times 100, and that's a pretty small percent. So it's definitely valid, very, very, very valid that we use this approximation. So now we can go through and plug in all of our equilibrium values, or calculate all of our equilibrium values. So our hydrogen is 0.025 plus x, and then we can plug in our teeny tiny value of x, but it didn't change it at all, right? So there is our equilibrium concentration. Our ethene is just equal to x, and then our ethane, we have 0.405 minus x. Again, that x is really tiny, so it doesn't change it even a little bit. Okay, so this problem was tricky because we needed to deal with the reaction first before we could deal with the equilibrium. And that will often be the case when you're being given concentrations of everything and they look approximately equal to you, right? If you'll recall, right, we had approximately equal concentrations or amounts of moles of everything, and we had this gigantic K value. So that doesn't make any sense, because if we had approximately equal concentrations of everything, we're going to have a really small K value. It might be just over 1 or just under 1, but we're going to have a relatively small, or, a value that's relatively equal to 1. The fact that this was gigantic tells us it should be mostly products. So we need to deal with the reaction so that it makes mostly products, and then we can deal with the equilibrium, okay? And that is the end of our lecture today. We have finished chapter 15, okay? Today's lecture was definitely the hardest one of the chapter, and it may actually help you to watch it all again and walk through the calculations a little bit slower, or walk through, each of the problems and do them yourself. Remember that you have a ton of practice problems on that chapter 15 lecture worksheet, and I've posted the answer key so you can see how they're done. If you have any questions on any of this, or if it was confusing, please ask me. Remember, I'm always available via Remind or email or come to my office hours. I am more than happy to help walk you through these types of problems. I do want you to know that right now we're just focusing on learning how to calculate equilibriums. When we start getting into the next chapter on acids and bases, I'm going to assume that you are all experts at these equilibrium concentrations, and we're going to use them to do acid-base calculations. So let me tell you, it doesn't get easier from here when doing these types of problems. So if you're struggling in this chapter, make sure you get help so that you can survive the next few chapters. Otherwise, they are going to be very, very, very challenging. Okay, guys, that is it for chapter 15. Send me all of your questions that you have. Otherwise, I will talk to you guys next time.